All right, so in this case, what we are doing is deducing our own rate law. So in the previous topic, we were given the rate law. Now we have to deduce our own. But here's the thing about rate law. Rate law can only be determined from experimental data. We have to have experimental data to find it. In this case, they've run the experiments for us. So we have data set here, okay? So let's build our rate law. So how do we do this? I always encourage you all always to pull the notes that are in the modules. I've tried my best to slim them down and simplify them and just put the important bits there. Okay, in the notes, it talks about how to deduce rate law from initial reaction data. So here we have a data set, and we have 1, 2, 3 trials. So trial 1, trial 2, trial 3. What they've done is they found the initial rate of the reaction when the initial concentration of N2 was this and H2 was this. This was the initial rate. All right, then we do a second trial. Let's change the initial rate. We half it or double it or triple it or whatever. In this case, they kept this the same, but here the concentration is reduced from what it was in the first trial. And in the third trial, the concentration of N2 is reduced and the concentration of H2 is also changed. Okay, so we've got different data sets here for each of the 3 trials. So how do we find rate law from this? Well, we have to find the order that each reactant is in individually. So how do we do that? Well, let's find the order that N2 is in. In order to do that, I need to find 2 data sets or 2 trials where the concentration of N2 is changed, but the concentration of H2 is held constant. I want this to be held constant because then I can eliminate, I can throw it out and ignore it because the concentration doesn't change. I want to see how does the initial rate of the reaction change when I change the concentration of this and leave this the same. Okay, so just looking, I see trial 1 and trial 3. Look here. In trial 1, the concentration of N2 was 1.35 molar and it's 0.272 molar. In trial 3. In trial 1, the concentration of H2 was 0.287 molar and it's 0.287 molar in trial 3. So that means I can completely ignore the concentration of H2 here because any effect on the initial rate will be simply due to the change in the concentration of N2. Okay, so let's look and see how the rate changed when I altered the concentration of N2. Here it was 100, and here it was 20.1. So the first thing we want to do, let's go here. Let's write a new page. I'm going to set this up like I set up the explanation for a previous topic. We have 2 rates, right? We have 2 rates, okay? So I'm going to call this one rate 1 and this will be rate 2. It's a smaller value. So rate 1 over rate 2. Well, what is rate 1 equal to? What's the rate law, right? How do we write a rate law for this reaction, this first reaction? It's equal to K, whatever K is, times the concentration of N2 times the concentration of H2, right? And I'm going to do the same thing for this second one. K2 is equal to, multiplied by the concentration of N2 times the concentration of H2. All right, so let's place in our information, okay? So what is the concentration of N2 in reaction 1? 1.35 molar. So let's place that in. Rate 1. What is rate 1? 100. So let's place that. 100 per second. What's rate 2? 20.1. 20.1. We don't know K, but we're going to try to find it. The concentration of N2 again was 1.35. 1.35 molar. And the concentration of H2 we're going to ignore, but I'll write it in just to be complete. 0.287 molar. Okay? It's the same for trial 3. It didn't change, 0.287. So I put that here. And in trial 3, the concentration of N2 was 0.272. 0.272 molar. All right, so again, this is all we've done. This is trial 1, and this is trial 3. Okay, and I've just substituted the rates and the concentration of N2 and H2 here. All right, I got that information from this table. Now, K, we're going to cancel out. Okay, it's a constant. It's going to be the same. K is the same as long as the temperature doesn't change. This is also the same, so let's cancel that out. So to simplify this, we get 100 divided by 20.1 is equal to 1.35 divided by 0.272. Our units look like they're going to cancel. So what we end up with is 100 divided by 20.1 is 4.975. I'm trying not to round too much. 1.35 divided by 0.272 is 4.963. So when I look at this, this tells me, all right, so when I decreased the concentration of N2, looks like I decreased it by almost a factor of 5. What happened to the rate of the reaction when I decreased the concentration of N2? It looks like it also decreased by almost a factor of 5. So what this means is 4.975 is pretty much or approximately equal to 4.963. They're almost exactly the same. And the differences between these two values is probably attributed to error in the data. What do I mean error? Well, these values had to be obtained experimentally, and somebody took those values and rounded these probably even. And so error is introduced just from the fact that they are rounding and from the fact that a person is taking these measurements. Okay, we are prone to error. So because this is about equal to that, if I want to know what the power, right? What's the power of this? Well, X must be equal to, what would it be? 1. 5 to the first power is 5. 10 to the first power is 10. 25 to the first power is 25. Because these numbers are pretty much the same thing, there's no need for this number to change at all. So X must be 1. It must be to the first power. So that means that N2 is in the first order. X is equal to 1. So N2 is in the first order. Okay, we've got our first bit of information for the rate law. Let's find the order that H2 is in. Okay, what order is H2 in? So we're going to do the same thing, except let's substitute values now for H2, where N2 stays constant, but H2 changes. So let me start a new page, and let's plug in here like we did before. Okay, so let me go back, and I've identified these two, this one and this one, is the data sets I want to use because the concentration of N2 stays the same, so we can ignore it this time, but the concentration of H2 changes. And I want to know what effect does changing the concentration of H2 have on the initial rate. Okay? So the concentration of N2 is 1.35 molar. So we don't know K yet. It's 1.35 molar in both trials. Okay, and we also know that this is to the first power, so we can go ahead and plug that in there. And the initial rate is 113.6 for the second trial. So I'm going to I always put the larger one on top. That's how I know what to place for rate 1 and rate 2. It's easier if you just place the largest rate on top and the corresponding rate law to go with that one. And it was 113.6. Okay. What is the concentration of H2 in the trial where the initial rate is 100? 0.287, and it was reduced to 0.106. All right, so let's go back. 0.287 for 100 and 0.106 for the trial where the initial rate was 13.6, 0.106, 100, 0.287. So now we want to know, all right, we found this. We found the power, the order that N2 is in, which we called X. Let's call this one Y. What's Y? Okay, we don't know, but let's figure it out. All right, so let's cancel out our constants. K is the same. We're going to cancel it out. This is the same. Let's cancel it out. And we also determined that it was first power. I put that in. First power, first power. So 100 divided by 13.6 is 7.35, and I'm going to 29. I'm going to write it out a good bit. I don't want to round too early. And that's equal to 0.287 divided by 0.106 is 2.7075. We want to know what Y is. So this one's just a little different than the last one because here I can't clearly see, right? I cannot clearly see the relationship between 2.7 and 7.35. It's not like this is double. Well, it's not quite, this isn't double that or quadruple that. So how do I solve for the exponent Y here? Well, I placed an example video also in the lecture videos of Professor Dave doing this exact same thing. What he says is that you can take the natural log of both sides to solve for an exponent variable. Okay, so when I take the natural log of this exponent becomes, we can bring it down here. So this would be the natural log of 7.3529 is equal to Y times the natural log of 2.7075. And I can just bring Y over. Y, or leave Y there and just bring this over. Y is equal to the natural log of 7.3529 divided by the natural log of 2.7075. Y is equal to, and I get in my calculator, 2.00. So Y is equal to 2 in this case. 2. That's our exponent. So that means that H2 is in the second order. So now that I know the order that each of my reactants is in, I can write a rate law. That's what they're asking me to do here. Rate is equal to K times concentration of N2, which is in the first power, times concentration of H2, which is in the second order. I meant first order and second order. Okay, we have our rate law. So now that we have our rate law, we can find K as well. K is equal to rate divided by N2 times H2 squared. And I can use any data set here. I can pick data set 1, data set 2, or 3. So I just take the information from the data set and I plug it in down here. So what shall we take? Let's take data set 2. Okay. In data set 2, what is our rate? Our rate is 13.6. In data set 2, what's the concentration of N2? 1.35 molar. And what's the concentration of H2? 0.106 molar, and that's squared. This is to the first power. So if I solve for K, I just plug this into my calculator. This divided by all of that. And I notice that this reaction is what order overall? It is third order overall. So my units will be, for K, will be some number, molarity to the negative 2 times seconds to the negative 1. So let's see what that number is. 13.6 divided by, open parentheses, 1.35 times 0.106 squared. And in this case, I ended up getting 897 to 3 significant digits, 897. Now, one thing I do want to point out here, and don't freak out if you're very thorough and if you try to find K from this data set like we did, or from this data set. What you get for K may be a little different. For example, I got 897. Well, ALEKS gets 899. But the data set that they use is data set 1. The reason that K may be just a little bit different from each data set is because each data set has its own amount of error. So there are going to be very, very small variations in K, but the general idea is K should be very close. So 897, it is very close to 899. And so now we have this, and we're done.